In this video, we will present system model of electric vehicle in SysML and integration with detailed design models coming through FMU standard, specifically of the battery model coming from Dymola, FMU functional mockup units, and using a functional mockup interface, and requirements verification in different contexts. So the standard allows us to export from 100 plus tools and interchange simulation as the black box and model data as a black box, and integrate them in different other tools. Like in this case, we are using SysML tool as the Cameo Systems modeler, and not only to integrate, but also to test that in the bigger context, detailed design model still satisfies requirements, the system still satisfies requirements, and do trade-offs, do different scenarios in which we want to test requirements. So for that, we need to develop architecture of the system, and we follow the standard process that we are designing the system. First of all, we start from the logical architecture, then detailed architecture, but when we get more details and we do analysis in specific tools, we don't know that this architecture stands correct against requirements. So we can import those detailed design models and test the same architecture which we created at the beginning. So we have here this architecture of the system, electric vehicle with powertrain, with motor generator, on board charger. We see here also intelligent power unit. We imported electric terminology, a small glossary here to see that we can use the terms and get the definitions. And then we see thermal system, which consists of part of that vehicle. And we also here we see FMU imported of the battery. So this FMU import is kind of straightforward. Once we have that's received from the analysis tools, we can just drag and drop it. And if this standard is supported, we will get it as a black box, as we can see here. Now, next step, what we did, it's actually connected to the context and environment. So we said, okay, the vehicle will be in a couple of contexts, charging contexts, when it is supercharged, and in this context, and in also in driving context, when the vehicle is driving during different environments. So in both contexts, a vehicle shall satisfy requirement of the battery temperature. Doesn't matter what are the environment temperature, what is this scenario in which it is going through, still the temperature should be between 25 Celsius and 35 Celsius. And we see that using natural language analysis, we can extract this constraint and constraint automatically properties here based on the text. So for example, if we are changing requirement 24, 34, and 26, we are constraining automatically with new parameters. Let's change it back if you want. And then once we run the simulation, we will get applied constraint, and we will know that this property failed, requirement failed or not based on those extracted dynamically constraints. So here we see in those environments, in driving context, we have environment which has road, and wherever road has elevation, wherever has wind and temperature, ambient temperature by default 30 Celsius. Also, the context is electric vehicle with all these parts, which comes from the logical architecture of electric vehicle or physical. And then here we see charging context, where in this context we see environment, but also charger, supercharger, residential chargers. Now, next step is to put the connections between properties and parts in those contexts. So let's say that we want to check charging context. So we have here speed of the pump which circulates water. We have mean temperature. We have of the cell which gets output from the battery FMU, And input into this battery FMU, we see here pump speed, power load, and ambient weather temperature. So weather temperature comes from environment, power load comes from powertrain onboard charger. So we, in this context, we want that charger would load the battery, right? So we did that, we connected here. And this is still this FMU, which we saw in previous here. But now it is connected to this context, to the charging context. And then let's check how it looks like that import of FMU, because we might connect, different FMUs together coming from different tools and see how that works and do trade-offs and do different situations. It's never that, for example, perfect characteristics of single component is the perfect in the system. It's never like that. It's only the combination which should satisfy all the requirements in different scenarios, and then also the optimal kind of combination based on the selected criteria. So we can test that before actually building some actual system. So now if I would want to import another battery, let's try to do this. I will take another FMU here and drag and drop. So this is what it requires, and it will start importing. Import process takes some time. And here we see this battery FMU imported. Now let's go in. We can delete all the properties which we don't want, because this is just like representation of the data. If we don't get this value, we just remove from representation. Now we have this second model of the battery, and let's say what it would take to reconnect it. So if we could take it and drop it on the existing, and you see connectors still available, so we can just create another configuration with different models coming from different sources. Still connections are available, and we can run this simulation model. In order to change it, again drag and drop. Here we see everything connected. Now next we did also driving context, and maybe before going to the driving context, let's see how we want to check that charging context. So for charging context, we wanted to create the charging pattern for supercharging. When we increase the power load, and we use state machine for that, we created inside of the charging context state machine, which triggers if supercharging is true. And we see states, and you see the power load is increasing every 30 seconds based on this pattern. After 4 minutes, it switches to different pattern. It's actually decreasing here. After 11 minutes, switches to this pattern. After 4 minutes, switches to this pattern, and 15 minutes to this, 20 minutes to this, and once power load is less than 20, switches pretty much off. Just like keeps the same power load, and then after 50 minutes from the beginning switches off. So we will reproduce the same pattern which we found from the specification here of the supercharger load, and we can see here this pattern should be reproduced in the simulation. So we will run it, and when we execute it, we can run in different also. Not only that we'll run this scenario, we can have many scenarios created quite quickly. For example, if I want another state here in the middle after, so we see here another state inserted, so 3.5, 3.5 state, and then at 16 minutes from the beginning, exit that state. So it will keep it. Let's say if I will not specify what load is this, it will keep the same load for last half of the minute, last minute, right? And then switches to this one, right? So we can do this kind of, if I would want to specify specific load, could go here, go to the specification of this state and say that I want specific load, power load plus 1. So we will see this kind of additional increase here at the end, where we will jump maybe like not one, but or maybe let's keep it one. Yeah. Okay. Now also what we can do, we can run with different configurations. So we can run in different temperatures. So 30 ambient temperature, 50, 40, 70. Here we can sort it, -10, 0, and pump speed 1. And here we can delete the uh, power pack cells temperatures. And here we see supercharger true, right? So we will run with those different configurations. First of all, let's run in one of those configurations. Let's say charging 50 Celsius temperature of the environment, and let's go through this state machine in this configuration. So let's run it. So we see here it follows this pattern, and as good as we created it in state machine. So if it is not perfect, so this is because we reproduced it not perfectly, but we can pretty much change everything, whatever we want here. And we see here, it drops now based on this one. And here it jumps a little bit because we created this jump, right? And then it goes back in this one and then goes down. And here we see the temperature. This is the cell's temperature, and we see which requirement is not satisfied. So during this time, the temperature was not in the range as provided by this requirement. So we see this highlighted in red, and also once we move mouse over, we'll see this red. We see which requirement is not. So we could track many requirements and see visually when which requirement fails. Just it's up to us how many requirements we want to put on what properties. So now I will stop simulation. I can save this chart uh, to the table. I can save it to the model. I can save it as the image. I can close it right now, and then I will run all the configurations at once. So because I don't want to wait and run each of them visually, I can run all of them at once without actual visual simulation. I will just see the final result. But final result depends also on us, what we want to see here. So let's run it, charging all, Python not. And this battery FMU is actually with internal thermal management. So if it sees that it's kind of goes too large load or something wrong, or like ambient temperature is too high, so it has cooling system, and so it depends on what kind of FMU you get, right? So here we see the output. So it managed charging load correctly, even with high temperature, ambient temperature. Here we see 70 degrees, right? And -10, right? Also still good. Now let's move to another context, so driving context. So in driving context, we connected also to the battery motor. Instead of the charger, we see here that motor provides the load, but also what we connected wind. It could be against the wind or by the wind, elevation, uphill, downhill, or also speed. So all those things, actually here we see that based on the function, input the load to the motor, it increases the load of the motor, decreases the load of the motor to keep the same speed. And again, we will run through a different scenario now in this case. So here we will see the state machine. So here we are running in suburb for 10 minutes. Then we are switching to the ludicrous mode. So we are increasing the power load to 450, and after 11 minutes, after 1 minute actually, we switch to uphill mode, and then after 6 minutes, so we see here this at, it means that from the beginning of execution, so it's not relative time when from beginning of this, but from the beginning of execution. So between this and this, it takes 1 minute to switch, right? So this ludicrous mode takes 1 minute only. So uphill then, elevation plus 20. This kind of what we use here, it's not some degrees, it's not actual speed, it's just a load based on that what we want to achieve. So we want to achieve ludicrous mode, so we put the load of 450 watt hours. If we want to kilowatt hours. If we want to do the suburban speed, we put here 20. Could be, translation, depends on the function where we want, how we want to model this. It's kind of very fast to model this scenario. We could model many different scenarios. You can do, like probabilities here with some kind of events happened. We could take maybe, even some existing terrain and put here based on the Google data. Here we see against wind, highway, and by the wind, and then we end this scenario. So again, I will run it, driving on in the 30 Celsius, or let's say 60 Celsius. Oh no, maybe 30 Celsius. Let's run it. And now we will see different situation. So we saw this load jump in this ludicrous mode, right? And we saw the temperature also jump here, cells temperature. But later it settled down, so everything went well. So we see that it is in the limit. Just we need to see that it will stay in the limit. But we can see here that it keeps in the limit. So let's stop it. And now let's run the same, but now in 60 Celsius environment. So kind of not very realistic, but still let's try. And you see what happens. So at the beginning it was not okay because the model was like that, and then later it was okay, and now it is again not. So requirements is not satisfied. Celsius, the mean temperature of battery pack, it's almost 60. And we could play with the, for example, we can check some other characteristics. We can say like, okay, we might want to powertrain PU battery, we might want pump speed to increase to the 3. And we see the temperature drops, right? So it makes sense to control that. Let's take one. And now we end of the simulation, right? So now let's come back and see that we actually has this in control. So we have those configurations here. And we have here those configurations. Pump speed everywhere is 0, right? So we might want to put something like 2 and see that it was enough. Also, this pump speed could be controlled automatically for sure, during the simulation. And this is one of the parameters which might be managed by some other model and controller exported from other tool even, right? So now let's run with the 2 and with those different temperatures. So we see from 20, 30, 40, 50, 60. And let's do this one now automatically. So let's run in more properties, mostly data affected this time, execution time, and we see results. And also we will get validation. So we see that this was okay, not okay, because temperature was too low. And then this was okay, this was okay, this was okay. Now, if we will put 3, let's just check the scenario, and then let's finish this demonstration. Be able to architect systems at the right abstraction level, at the same time test that they will work. So here we see with this pump speed increased, we see better situation. So this ambient temperature will be still satisfying requirements. Still not the case with other temperatures. And here the last piece, what we wanted to show is the glossary. Once we imported to the glossary the data, here we see that we have terminology as electric vehicle, EV, and for example, like here, quick charging and all other terms. And if we want to use those terms, like here we see, you see this is underlined, and we can move mouse over and see this. If we will want to add FMU as the part of the glossary, so add to glossary. Here you go, now it is part of the glossary. We can move mouse over, go to the glossary, specify definition functional mockup interface. Now, if we will go back and move mouse over, I would see here that its definition is here. Functional mockup interface. If I want to use some term in order not to identify by myself what is this term or whatever, I can use start typing and use control space and choose term from the glossary. So here we have it. Okay, thank you for time.